Good afternoon, data managers. Welcome to the video on measures of central tendency. This is something that we've all learned about. Mean, median, and mode are parts of the regular everyday language that we use. So we're just going to take a quick look at these three concepts. I'm sure you've seen them before in science class and in your math classes. So the most common measure is the arithmetic mean, followed very closely by the median, and then a little more distantly the mode. So, the key concepts that we need to know. First of all, the mean is going to be an average, the arithmetic average, of all the values in a data set. So that means we add all the values up and divide by the total number of values. The median is slightly different. It's the halfway point. It's the 50th percentile. And that means you're going to have your data arranged from lowest to largest, from least to greatest in an array. So again, the median is the halfway point. The mode is slightly different. It is the most frequently occurring value in a data set. So it doesn't necessarily have to have anything to do with the median or the mean. Okay, so first things first. Let's recall the difference between the sample and the population. So when we take a sample, we're measuring central tendencies, or we're measuring other statistics, and we're trying to approximate actual population values. Now, why would we do that? Well, it's much cheaper to take a sample, and quite frequently we simply cannot get population data. It's simply impossible. Or I was going to use a Simpsonism, impossible. Now, first of all, the mean. So the mean is the sum of data values. So you add them all up, and then you have to divide by the total number of data values. So when we're talking summation notation, we have a sample mean, and we can write it as follows. X bar is the summation from I equals 1 to n of each of the values, that's x sub I, all over n. And you can simplify it by writing sigma x all over n representing sample size. So in this case, x bar is the mean of the sample data set. The way we say it is x bar, x with a line written over top. X sub I is each of the individual values of the sample data in our array. And sum of x is going to be sum of all of the individual values of the data. Now, this is stuff that you've done since grade 8. You've been summing them up manually, and you've then been dividing by this total number. Okay, so this is your sample mean. The population mean, pretty much the same formula, except instead of dealing with x bar, we're dealing with the Greek letter mu. It looks like a U with a little line starting off the first vertical bar. And then replacing n, lowercase n for the sample size, we've replaced it with uppercase N for the population size. And there are the individual values.
Good afternoon, Riverdale. If you have not already sent down your attendance folders, please do so immediately. Thank you.
So, I'd like you to notice how the symbols change. When we're dealing with population, we're using the Greek letter mu, and we're using capital N. When we're working with samples, we use x bar, and we use lowercase n. Essentially, they're the same. However, there are subtle differences, and these differences are especially important when it comes to doing standard deviation. We'll learn about that in a lesson or two. So, let's start off with an example. Calculate the mean of 5 numbers, 6, 4, 10, 7, and 3. So, we're told that this is a sample, which means we are going to use the formula that uses x bar and lowercase n. And since we have 5 data values, we also have an n equals 5. So, we start off with our sample mean formula. X bar equals the summation of x all over n. And we plug in our values. 6 plus 4 plus 10 plus 7 plus 3, all over 5. And when we expand and simplify, 30 over 5 equals 6. So the mean of this group of numbers is 6. And then, of course, being good Data managers, good scientists, you will write a concluding statement. Thus, the mean of the sample test scores is 6 marks. Now, next concept I'd like to cover is the weighted average, the weighted mean. You can call it either. Common parlance is to use weighted average, but I guess technically it's the weighted arithmetic mean. And this is when objects have different weights in terms of their overall contribution to the total. So for example, when you're talking a 30% exam and 70% term mark, that is a weighted average. And you're going to have to excuse me. So continuing, the weighted average, the weighted arithmetic mean, we use that when we have objects with different weights in terms of their overall contribution to the total. So the classic example is the 30% exam, the 70% term. Now you'll notice that on the left we have the formula for the sample, and on the right we have the formula for the weighted arithmetic mean for the population. Both of them simplify to the exact same formula. The sum of f times x all over the sum of x. For those of you who have done calculus, please note that this is not a function, it is merely a frequency. So, again, on the left we have the sample, on the right we have the population, and you'll notice that we do have some new variables in here. We still have the familiar x bar, the lowercase n, the mu, and the uppercase N, and the x sub I. So those are the exact same as what we're used to, except now we've introduced this concept of weighting. So W sub I is the weight that's associated with each data observation. Another way of dealing with this is by using frequency. So instead of using the weight, we can also use the frequency. Frequency is the number of times that each value occurs in the data set. So continuing, my apologies for the interruptions. Once again, we have the weight that's associated to each data observation. We also could use instead the frequency, or the number of times that each value occurs in a data set. So when we do that, we can have f times x, which gives us the weighted values of all of the observed values. I hope it becomes clearer after we go through an example. So let's take a look at a frequency distribution with weighted means. So in this case, we're dealing with a sample, and our sample has a number of values in it. So we've got scores of 45, 50, 55, 60, all the way up to 85. Each of them is assigned a frequency. So in this case, that means we have 7 items, 7 objects that have a score of 45, 12 objects with a score in 50, and so on. You can see the pattern. Now, we start with our weighted mean formula. X bar is the sum of f times x all over the sum of f. So let's take a look at what that means in practice. So here is the expansion of the two summations. Now, let's take a look at the first pair of data. We've got a score of 45, which has a frequency of 7. Now we take that, we transfer it into our expansion of the summation. We have 7 times 45. We will need to do that for each of the pairs. So we've got 7 times 45, 12 times 50, 36 times 55, and so on. We add all of those multiplications up, and then you also have to remember that you're dividing by the sum of the frequencies. So in this case, our first frequency was 7. It goes on the denominator, and then we're also going to add all the other frequencies together. In the end, we end up with our weighted mean. In this case, it's 64.8. And then, of course, you do have to have your concluding statement. The mean test score of all 300 students is 64.8 marks. Now, we can simplify our life. That's why we've learned summation notation. Some of you have asked, what is the point when you could use an expansion formula? Well, take a look at the one on the left. So the one on the left is an expansion of the summation. On the right, we have another expansion of the summation. Same thing, we're missing some details there. However, once you've established a pattern, you don't need to go into all that detail. So my recommendation is to use the format on the right once you understand the pattern. Now, frequency distributions. My apologies, I just realized I used the wrong term on the previous set of slides. Those were frequencies. These are frequency distributions. When you're using class intervals with your frequency distributions, you end up having to use the midpoint of the class interval. And we always calculate the midpoint by using the mean formula. You've already done this with percentiles. That's exactly what you do in percentiles. So in this case, let's take a look at our data set. On the left-hand side, we've got a table, and then it's reproduced on the right-hand side with some more information. So on the left-hand side, we have measured the height of a number of people. Their heights range from 150 to 180. We've measured the heights for 50 people in total. What we've done is we've created a frequency distribution. We've created these bins or classes. And we've said that everybody from 150 to 154.999 centimeters falls in this one category. Four people do that. And then we've got people from 155 to just under 160. We've got 7 people who fall into that category, and so on. Now, when we are trying to figure out a mean, we don't know the individual data points in these cases. So what we have to do is we have to take an aggregate. And in the case of 150 to 155 centimeters, we take the lower limit and the upper limit of the class. We sum those two together, divide by 2, and we get the midpoint. So in this case, 150 to 155 centimeters, when you average those two values, you end up 152.5. And what you are assuming is that all 4 individuals in that class have a height of 152.5. They obviously don't, but they have a height of 152.5 for the purposes of figuring out the mean for this whole frequency distribution. In this case, we are working with a population, so our formula has to be adjusted to include the particular variables we use with a population. So we got 150 to 155, average of 152.5, and 155 to 160 with an average of 157.5. Now, since it's a population, we're using mu, but that's pretty much it. And the way that you write this kind of mean calculation is that you're using, instead of fx, you're using fm, m representing the median, or the mean, my apologies. So we've got mu equals, approximately equal to the sum of f times m, the frequency of the mean times the mean, all over the sum of the frequencies. So just like before, we take the individual values. We've got 4 times 52.5 on top. Let's take a look at where they come from. We got 4 individuals, and we're assuming that each of those individuals is 152.5 centimeters long. And you do that for each of those pairs on the numerator, and then the denominator, like we did before, the sum of the frequencies. So you're going to sum up all of those individual frequencies. So we've got 4, 7, 18, 11, 6, and 4, which in the end should give you 50. So that is figuring out the mean of a frequency distribution, where you've got classes rather than individual data points that you can point to. Now, what about the median? That's the second type of a measure of central tendency. So the median is the 50th percentile. You've done it. That's the last video we did. So again, we've got a sample median versus a population median. And all you have to do is replace the lowercase n for the sample with the uppercase N for the population. And the formula for the median is merely the position number of the 50th percentile within the array. So that'll be n plus 1 times 50 all over 100. N representing the number of items in the sample. Okay, now for the median math, we've already gone through this. It's no different than what it was a few days ago. Okay, so here's a very important question for you to ask yourself. Which measure of central tendency should I use? There are no hard and fast rules. Well, actually, you will learn some if you go on in statistics, there are some requirements, some assumptions that people make in certain cases, but we're not going to go into those. Now, first of all, let's take a look at the notion of outliers. Here we have a nice data set. We've got a bimodal distribution, and we've got some outliers on the upper end. What those outliers do is they end up affecting the mean. They pull the mean up or down, depending on your data set. So if the data is containing outliers, chances are you are better off using the median rather than the mean to represent the data. So let's put the circles around there. Outliers will affect the mean the most, thus we use the median. Now, if we have data that is strongly skewed, and take a look at the outlines that just appeared around the graph on the bottom. So we can have a negatively skewed distribution and a positively skewed distribution. So if the data are strongly skewed, again, we may very well be better off using the median to represent the central tendency of the data. So the mean in a negatively skewed frequency is too low. In a positively skewed frequency, it is too high to represent most of the data points, while the median does a pretty good job of cutting the upper half and the lower half and representing the midpoint. Now, finally, the third consideration, if you have symmetric data, that means you've got as many items below the mean or median as you do above, then you're going to have a median and a mean that are close. So either is appropriate. I will point out that in this case, you are most likely to use the mean, because the mean allows you to do certain computations that you cannot with a median or and definitely not with a mode. Now, if frequency is the most important measure, so examples are shoe sizes or city population sizes, then you should use the mode. So take a look at the population statistics for cities under 100,000. We've got here a nice frequency distribution of the size of cities and the number of cities. The size of the cities is on the x-axis, the number of cities on the y-axis. You'll notice that the most common size is quite small. The median size, so the halfway point, is a little bit larger, and then the mean is quite a bit larger. Now, why would the mean be substantially larger than the halfway point or the most common point? Well, because you've got some cities that are really, really, really big and they pull up the average size. So we could take Ontario as an example. We have Toronto as the largest city in Ontario. It's got a size of 2.5 million. And if you were to factor in the GTA, a size of 6 million. So out of a population of 12 million people, 50% of Ontario lives in the GTA. And about just under 25%, more like 20%, live in Toronto alone. So if you look at Ontario's city size, you would have a very large mean city size, but we've got a lot of much smaller cities, so our mode would exactly fit this nice little graph here. Okay, so that's it for today. My apologies for the interruptions. Let's hope that you can make use of this.